Greetings everyone. So this video is going to cover a little bit about the Calculating Forces classwork that I asked you to complete this Friday. This is just kind of a review video. Remember, these notes are really just a chance for you to practice problems. They'd be the equivalent of class if we kind of spent 45 minutes and I just kind of had you working in groups and you were kind of practicing these different questions and putting the answers up on the board. All right, so that's kind of what these notes are for today. So I'm just going to talk through a little bit about what exactly my thought process was and kind of what we're looking for to answer these questions. All right, so starting on the first page, you'll notice, of course, you can already see plenty of the answers. I'm just going to kind of work through a little bit what my thought process was for them. I'm not going to go through every single question because some of them are basically the same thing, just the same process. But let's start with the first question, which says draw an FBD for a hanging mass that is held up by a string. Now, I didn't give you a picture, but sometimes you got to be able to visualize what's going on here. And we've actually asked this question before multiple times. All right, so in this case, kind of thinking about it, if it's just being held up by a string, we're thinking about the forces that are pulling on it. Well, we know that it's got to be gravity, and we know that there's probably tension pulling up on the hanging mass, all right, that's keeping it from falling. So there's going to be two forces, gravity pulling down and tension going up. Now, you'll probably notice on your note sheet, the dot is gigantic. It'll probably get smaller when you go in there and edit it, but I had to work with what I got because I was writing on the actual homework sheet. But clearly, again, we're just looking to see what is pushing and pulling. All right, in this case, we just have two forces that are pulling. One's pulling down, one's pulling up. That kind of dictates what we do for our FBD. All right, now the whole next piece and this kind of whole rest of the page is all focused on the two formulas that we have focused on the last two labs. So the spring force formula and the formula for calculating the force of gravity. All right, now these first two questions, says what unit does mass need to be in to calculate weight? Now we talked about this at the end of the lab, kind of our notes section, but again, just remind ourselves, to calculate weight correctly, we need to make sure the mass is measured in kilograms. All right. Now, usually it's not a problem. Most times you'll see it in kilograms, but occasionally you're going to get it in grams instead. So in order to convert, you need to basically take how many grams there are, you divide that by 1,000 and it puts it into kilograms. Just kind of a little reminder, 1 kilogram equals 1,000 grams. Next question is what unit does the distance a spring is stretched, squished needs to be in? So basically what it's asking is, if I'm trying to measure how far I've stretched or squished a spring, what should I measure that in? All right. Now, normally you're going to measure it in centimeters. All right. Now, I wrote meters down here because you're probably going to, depending on what the spring constant is, which remember is just that number that tells me how much force it takes to stretch a spring, 1 meter. That will most likely be in meters. So you'll have to turn whatever you measured into meters. It really depends on how I give you the spring constant. But pretty much we can assume, just to make things easier, you're going to measure it in meters. All right. Now, number 3 is a bunch of calculation questions, all right? And they're all related to the same thing. I want you to calculate the weight of each of these objects, all right? Now, I don't explicitly say where we are, but if I'm kind of just going to say calculate the weight of something, you can assume we're on the Earth. Now, if you remember from last class, and remember from the lab, we came up with a method for calculating the weight of something based off of two different factors, all right? Remember, we came up with this formula, Fg equals m times g, where m represents the mass of the object, and the little g represents the gravitational field of the Earth. All right. Now, the official gravitational field of the Earth is 9.8 newtons per kilogram. For those of you in AP, you'll remember I told you that for calculation-wise on the AP exam, you can use 10. All of my calculations here are just using 9.8, just to make sure they're actually accurate. All right. But if you went through and did this with 10, and your answers are close, that's fine as well. Now, in all these cases, we did a couple practice problems last time, but kind of just to cover it again. We always start by writing out the formula. Then what we do is we basically fill in what we know and what we don't know. Well, what's nice about for all 4 of these questions, we are looking for the same thing, Fg. So we can start by just leaving Fg as it is. So all we have to do is replace the mass with whatever mass it tells us in the question and the gravity field, which is going to be the same in all 4 cases because we're always on the Earth here. So if we're looking at the first one, Fg equals m times g. The mass is 10 kilograms. The gravitational field is 9.8 newtons per kilogram. So do some multiplication. You're going to get that the weight of this object is 98 newtons. All right. Now, going through all these different things, I'm not really going to kind of explain how I answer these questions because I'm doing the same thing. The only one I will address is the last one. All right. It just says once again, find the weight of a 92-gram object. This is the only question of the 4 where I did not give you the mass in kilograms. I gave it to you in grams. So you notice I had to go through an extra step where I converted the grams, 92, to kilograms by dividing that 92 by 1,000. All right, and that's something you should have seen in chemistry, and it's kind of just some dimensional analysis, and that's something we need to be a little comfortable with because occasionally you're going to have to convert from one unit to another. All right, in all these cases right there, the first one, it's got a weight of 98 newtons. The 4 kilogram object, 39.2 newtons. The 0.48 kilogram object, 4.7 newtons. And for the 92 gram object, only 0.9 newtons. All right. Again, in all these cases, we're using this brand new formula, Fg equals m times g. Remember, the mass is the mass of the object. And as long as I don't explicitly say otherwise, you can assume the little g is 9.8, which is the gravity field of the Earth. All right. Now, the last part of this covers the other formula we discussed, and this is from the spring force lab. All right. Now, remember, once again, we talked about this formula. Spring force, how much force a spring is going to push or pull on something, is dependent on two things. It's dependent on this thing we call the spring constant, which, remember, is basically how stiff a spring is. Something that has a very high spring constant means it's very stiff. It's very difficult to squish or stretch. All right, so it's dependent on that. And it's also dependent on how far I stretch or squish the spring. All right. Now, again, we're going to go through and do it kind of the exact same way we talked about here. You're going to write out the formula, and you're going to look for what you don't know and look for what you do know. So, remember, I'm going to have Fs equals K times X. I'm going to replace this up with what I know. I'm looking for the spring force, so in all these cases, it's always Fs. And I know that I'm actually dealing with the same spring every time. So the spring force is the same. And it tells you, or the spring constant, excuse me. And it tells you up here, the spring constant is 100 newtons per meter. And again, just to give you a little context, that means it would basically take 100 newtons of force in order to stretch that 1 meter. All right? So for the spring constant, the K, you put in 100. Then for the X, look at how far we stretch it. So the first question, it says I stretch it 2 meters. All right? Well, I plug into my formula. 2 meters times 100 newtons per meter, it's 200 newtons of force. So if I'm going to stretch this spring 2 meters, it's going to exert 200 newtons of force back on my hand, if that's how I'm stretching it, because it's trying to go back to the way it was. The other questions work exactly the same, all right? Stretch 4 meters. 100 times 4, 400. This one, however, says I stretch it 55 centimeters. Again, we're doing this little thing where we have to do some conversions. All right, and you got to think a little bit about kind of the prefixes. Kilo means 1,000, centi means 100. So if I'm going from centimeters to meters, I need to divide by 100 to get to meters, which is what I've done right here. All right, so 55 centimeters, I turned it into meters, and then I multiply that by 100. So once again, the spring force in this case is only 55 newtons. All right, so in both these cases, again, we're just practicing using this formula. And it's not trying to be complicated. It's not asking us to do a ton of stuff. It's just going through and looking at it and saying, write down the formula, write in what I know, look for what I don't know. All right? Now, for the 2 questions on the back. These 2 questions are kind of a mix of all the different things we've talked about. All right? So there's some FBDs, there's some calculations, and there's some thinking going on as well about what these all mean. So for the first one, there's a box hanging from a string as shown below. All right? Now, I'm under the assumption that you have probably already done these problems, so that's why I'm not really taking time for you I'm not really having you take time to pause and answer the question. So, if I'm looking at this, amazing. This question sounds exactly like the question up here. All right, so again, FBD, it's hanging at rest. It's got gravity trying to pull it down, and the only thing keeping it up is the string. So I've got an FT going up, FG going down. All right, now, the next piece, it says draw a force web for the box. Now, again, we did a little force web practice on Wednesday and Thursday. Academic, we didn't get a chance to do this, so this kind of is your force web practice. When we draw a force web, we start by drawing a circle that represents the object we care about. So in this case, it's the box. All right. Then we start drawing circles for every other object that could be pushing or pulling on the box. All right. So in this case, we have the string, we have the earth. Those are really the only things that matter. If you want, you can also do a circle and put the ceiling, because technically the ceiling could be doing something that might be helping out the box. We're not really sure. But if you want to put the ceiling as well, that's totally fine. But once you've drawn those 3 circles, we then need to connect them with lines to signify that there is a force acting between them. All right? Earth is usually very easy because Earth always acts on everything. So we just draw a line from the Earth to the string and the Earth to the box because the Earth is pulling with gravity on both of them. And then between the box and the string, there is also going to be a force, as we kind of saw up here. And then the last piece, once you do that, you just label the forces. Once you've done all that, in order to make sure that you know which object you're looking at, just draw a dotted little circle around the one that we care about. In this case, it's the box. And by doing that, we can clearly see, look at our FBD, there's two forces. Look at our force web, two lines going into it. So those should match to make sense here. All right. Next, I asked you to calculate if the box has a mass of 5 kilograms, what is its weight? Well, again, going back to what we did above, you just start by writing out the formula for FG. FG equals M times G. Again, I'm looking for the weight, which is FG, so I'm just replacing it with the other stuff that I know. I know the mass is 5 kilograms. I know little g is 9.8. So 5 times 9.8, you're going to get that the weight of that box will be 49 newtons. All right? Now, I asked you a question we haven't really asked before, but I want you to think a little bit. If the string can hold 40 newtons before it breaks, what will happen in this system and why? So, the question here is basically, if I hang this box off this string, will it be able to hold it? And if we think about the weight of the box, which is 49 newtons, and we think about how much force the string can pull back with before it breaks, we can see that this probably is not going to work. It will break. Since Fg, the weight, is greater than the maximum force of tension that can be exerted, basically it's the breaking force of the rope, it's going to snap because it can't support all of the weight. All right, and again, that's kind of just an important thing to think about. We're going to start focusing on this idea of breaking force as we kind of go in the next couple weeks. But this is our first taste of thinking about how that works. All right, now for the very last question. Again, same setup as before. I have a diagram. I want you to draw an FBD. I want you to draw a force web. Again, you've seen this picture before. Amazing. It's a box hanging from a spring. Almost seems like it's just like this one. I've just swapped out whatever's holding the box up. So the same things are applying here. There's still going to be a force of gravity trying to pull the box down. And in this case, you're going to have a spring force trying to pull the box back up so the spring can go back to the way it was. All right, so you have an up vector and a down vector to represent an up force and a down force. Next, I asked you to draw a force web for the box. Well, again, just like we did before, you need to start drawing some circles to signify which object could be exerting a force. Start with the box, then the earth, and then the spring. These are all different things that could be pushing or pulling on the box. Again, if you put ceiling as well because you want to be thorough, that's totally fine. It could be the ceiling. For right now, we only really care about these three objects, though. Once we do it, just like we did before, we draw lines between them to signify that there is a force acting between them. So again, the earth is pulling on the box and the spring with gravity, so line right there, and put Fg. And the box and the spring have a force between them. It's this spring force, all right? And once you know that, just put a little dot circle around the box so that I know that's what you're looking at. I'm going to tell you right now, if I ask you to draw a force web and you do not put a dotted circle around the object that I'm talking about, you will get points off because that is an important part so I know what we are looking at. Then finally, look at the very last one. I said if the box has a weight of 30 newtons, how far will the spring stretch? All right. Well, looking at this question, we want to kind of think about the fact that, again, I'm talking about spring force here. So we're talking about spring, so I want to probably write the spring force equation. All right. So the spring force equation is the spring force Fs equals K times X, the spring constant times the distance stretched. This time, I'm looking, of the three things, I'm looking for how far it's going to stretch. I'm looking for X. All right. I know the spring constant. It tells me in the above. So I can replace that with 15 newtons per meter. And the spring force is going to be equal to 30 newtons. And it's because, if we think about it, if gravity is pulling down on the box with 30 newtons, well, since the box doesn't seem to be going anywhere, it probably makes sense that the spring is pulling up with the same amount of force, which in this case is 30 newtons. So the spring force becomes 30 newtons. 30 newtons equals 15 newtons per meter times the distance it stretches, which means when all said and done, this is going to stretch 2 meters. All right. Now, this is a quick little review. It's just, honestly, this is just a review problems. It gets us a little more comfortable, hopefully, with calculating some forces, using FBDs, and using these force webs. We're going to keep working through these all next week as well, even though next week is kind of a shortened week because of the election day kind of days off. With that being said, if you have any questions, please do not hesitate to come to office hours to kind of ask me what's going on. You are not turning these notes in, so please do not ask me where to submit them. They are your notes, your practice, and we're going to keep kind of building off of these for the next couple of weeks. So with that being said, y'all, have a great rest of the day, and I'll talk to you later.